It's good. Yeah.
Okay, we've got 1:30. Why don't we get started? Good afternoon, research methods.
Good afternoon.
Oh, we can do a little better than that. Good afternoon, research methods.
Good afternoon.
All right, that's our orienting response. Welcome to week number 11, making our way on through. Today we're going to be talking about repeated measures designs. So I hope you're well rested and got plenty of REM over the weekend so that we can tackle this thing. Okay, so when we left off on Friday, we actually had a fun exercise. We had a couple of folks who were out, so just for their benefit, I wonder if we can have somebody explain a little bit about the experiment that we did in class using CogLab. Can somebody get us started on what that experiment was investigating and what some of the variables might have been? Or just what was it like to be performing that task? Any description might help the folks who were not in the classroom that day. Okay, thanks, Natalie.
We were looking at reaction times.
Oh, okay.
We were trying to find a green dot.
Okay.
And they would either get it with blue squares,
Mhm.
and then it got harder and it was with green squares. So it was definitely harder when the green squares were in there. Like I had to look over it like a few times.
Okay, really good. Yeah, really good. So this was a visual search experiment that we ran on a piece of software called CogLab. And our dependent variable, as Natalie correctly pointed out, was reaction time. And we were trying to find a particular target. It was a green circle. And on some of the earlier trials, that was really quite easy. It was a green circle among blue squares, right? Couldn't be simpler because the shapes were different between the target and the distractors, and the colors were different also between the targets and distractors. But then as we went on, the set sizes got a little bit larger, and we also had a greater target-distractor similarity, and trying to pull out that target from more similar-looking distractors was a little bit more difficult, and that presumably would have generated some kind of increase in reaction time. Okay? Anybody else want to add anything to that description? Okay, so our dependent variable was reaction time. Can we begin to try to name some of the independent variables that might have been there? There were actually a few of them. Anybody want to try to guess what some of the independent variables were? Okay, thanks, Skip. Okay, right, so on any given trial, there's sometimes relatively few items on the screen, other times there are many more items on the screen. So we sometimes call that set size. That's how many items were in that set on a particular trial. So set size is going to be one of our variables. And then maybe the type of search. We had certain kinds of searches where it was just one green among many, many blues. Other times it was a green circle among some green squares and blue squares as well. So we have different kinds, and we call those feature and conjunction searches. You don't need to mention that now or jot that down now, but in just a little while, maybe as we're actually a little later on today, we'll go on and take a look at some of our own data, and maybe we'll run a couple of analyses on what we collected on Friday, and certainly we'll be looking at that very carefully for tomorrow's session. Okay, so we're setting up a within subject ANOVA, and this is a repeated measures kind of design. Okay, why don't we get into our conversation for today? I did see that a good number of people had watched the video, so thank you for doing that. I don't think all of us watched the video because I know a couple of those were mine, and we were at 17 when I watched it earlier this afternoon. So a few of you perhaps hadn't watched it, but thank you for those of you who did watch the video. And what I thought we might do is see if students would like to begin responding to some of these pop quiz questions. We had several of them as we were getting started. And maybe we can open this up for the floor. We'll see if somebody would like to walk us through this. In your own words, can somebody contrast a repeated measures design with an independent groups design? Anybody want to help us out with that? We'll go with Brittany and then with Meg.
With your repeated measures design, you're utilizing the same groups in each particular, so you're using the same control group or same experimental group or whatever.
Okay. Okay, right. Actually, there's only the one group, right? And that group is measured repeatedly, measured time and time again across the levels of the independent variable. Okay, Meg, did you want to add anything to that? So we're contrasting repeated measures designs with an independent groups design. I think.
Yes, the repeated measures design, like each individual participant experiences like all of the levels of the independent variable.
Okay.
Versus the independent
Yeah. Okay, nicely stated, and that's really another way of stating what Brittany was saying. So 2 different ways of looking at that. It can be helpful to think about this from the perspective of a given individual in your study. Is that individual receiving all levels of the independent variable? And if so, that independent variable is administered in a repeated measures manner, which we might call a within subject manner. On the other hand, if that person is experiencing just one level of the independent variable, then we would call that a between subjects design or an independent group design. Who's okay with that? Anybody like greater clarity on that? That's something that you probably did in Intro to Psych, but we want to make sure it's really clear here as we're moving forward with some of the stats in just a little while. Please go ahead.
For the independent design, the group design, when like I know that each participant's only like experiencing one level of the IB, but can there be multiple levels of the independent variable and the like participant is only like experiencing one? Like whether, even though like, say there's like A, B, and C, like some of them are experiencing A, but they're only experiencing A, they're not experiencing B.
Right, that would be the independent subjects design. So you're getting only one level of that independent variable. What we haven't tackled yet this semester, and what we'll be doing this time next Monday, is what happens when you have more than one independent variable. But for the moment, we're just doing the one-way analysis, and we've talked about that before, and we have now multiple levels of our one independent variable, and we could administer that independent variable either between subjects or within subjects. Okay? All right, so that's a relatively straightforward one. Can somebody begin to speak to the primary advantage of repeated measures designs? There's actually a few of them that our book talks about, but we might talk about the primary advantage. Why don't you go ahead, Jenna? Thank you.
It allows us to remove individual differences
Okay.
from the analysis, which helps us better see the effect of the independent variable.
Okay, we can remove consistent individual differences. Maren also had her hand up. And did you want to add anything to that, or was that the primary advantage that you wanted to speak to?
No, that's it.
That was it? Okay. Mira has something else. Okay, that's another advantage. So the primary idea, again, is that we can remove consistent individual differences, right? So that we can figure out that maybe some of us are better performers than others, and that's not directly of interest scientifically. We want to understand how the conditions are changing behavior, and so we want to factor out the consistent individual differences. Mira's pointing out another possible advantage, and that is, in most cases, we can recruit fewer people or fewer participants, whether they're people or some other kind of animal, and we can come to the same conclusions using fewer participants, and that can be more efficient in many cases. It's not always true that we would need fewer of them, but it usually is true that we would need fewer, so that can be an advantage as well. Any other advantages associated with a repeated measures design? So we can remove consistent individual differences. It might be that it's a little bit more efficient because we need fewer folks. Sasha's got another idea? Okay, perfect. Okay, so frequently we're interested in how behaviors, thoughts, or feelings might change over time. And if that is one of your interests, then this would be the kind of design for you. Even within a given organism, we want to measure the change in behaviors, thoughts, and feelings over time. And this would be that type of design. Okay? All right. Any other questions or comments on those? Yeah, please go ahead.
I'm still just a little confused about like what you mean by removing like the individual differences.
Perfect. Okay. Let's see, and thank you for that, because this is a major motivation. Later on, we're going to be doing a computation on how we remove consistent individual differences. So it would really help us if we all have a very good intuition about this. Okay? We'll start out with the example that I've used a couple of times. We're going to pretend we've been hired by Spalding, and we have these differently colored baseballs, and we want to know if they're equally easy to hit. Okay? And it might be the case that I'm one of the participants, and so is one of the participants coming from the Boston Red Sox. Okay, that person's going to be a better hitter than I am. Okay, right? So if we're throwing white or blue or red or baseballs my way, it might be the case that the green baseballs are most easily hit. Okay, if we had a between subjects design, and I was the guy in the green condition, and one of these Boston Red Sox hotshots was in a different condition, we would have a huge difference between our performance just because he's a better batter than I am. And that's not really scientifically what Spalding has hired us to answer. They want to know which of the colors is easiest to hit. Does that work for us? Okay. So there is it doesn't matter whether you throw the Boston Red Sox player a white, green, blue, or red baseball. That player is going to be better than me. He's consistently better than I am. Okay. So there's some variability in our performance. He's better than I am, but that's just because he's a better hitter. It's got nothing to do with ball color. If we could somehow grab that difference, the fact that he's reliably better than me, he has that consistent individual difference relative to me. If we could quantify that and pull that out of our analysis of variance, then we could begin to look more precisely at the ball color effect. Does that help?
Yeah.
Okay, all right. So yeah, it's a good question, and we'll come back to it time and time again. And that particular item probably doesn't get talked about a whole lot in Intro to Psych. I'm sure they told you about within subject designs and between subject designs, but it wasn't really a good moment in time to be talking about how to partition variability in Intro to Psych. This is something that we reserve for maybe the second half of research methods. Okay? All right, let's go on and see if we can get through a few more of these. Psychologists use the phrase practice effects in a relatively particular way, maybe very differently than people might use that in everyday life. Improvements or impairments in behavior. Can somebody explain why this is? Anybody want to help us out with? Okay, why don't we go with Katie?
Well, when you're doing something over and over again, like a change is going to occur, but with like whether for the better or for the worse,
Okay.
you don't know. Yeah, but it's just like changes due to like doing something repeatedly.
Okay, right. So if we're doing something repeatedly, it might be the case that we actually get better, right? Because we become more familiar with the stimulus, we become more familiar with the task. We might develop a strategy, we might develop a motor skill, performance might get better, and we often think of that behavioral improvement as a practice effect, but it might also get worse. Why might it get worse? Katie's given us the hint that it might get worse. Why might that be the case? Yeah, okay, thanks. Okay, it might be bored, it might be that you're fatiguing. If it's a repetitive perceptual task, maybe you just are starting to tune out and you're not attending as much. If it's a repetitive motor task, it might be that your hands are getting tired, or whatever motor aspect of your performance is being measured. We might have some fatigue there also. So behavior changes with repeated measures, and we call that entire ensemble of changes practice effects, whether they're improvements or impairments. Okay? So we hope to engage in some counterbalancing to control for these kinds of practice effects. Okay. I wonder if somebody can help us out with this. On the topic of counterbalancing, can somebody explain the difference between complete and incomplete designs? This is subtle. We'll give Maren the first shot at this. Yeah.
Well, in complete design, each participant is exposed to the IV one time, so you counterbalance between participants.
Right, okay.
And then the complete one, they receive the IV many times, so you can do it with the individual scores.
Right, very, very good. Okay, so for those in the back who might not have heard that, what Maren was mentioning is that in the incomplete design, it might be the case that because this is still a repeated measures design, every individual is still going to receive all levels of the independent variable, but here it might be that you, as the participant, receive all levels of the independent variable one time only. And you get one time only. So if there are 4 different levels, you'll get each of those levels exactly one time. Okay? And because of that, we don't have any particular way of counterbalancing that within Maddie, for example. Maddie might be one of our participants, and we can give her all 4 levels, but because we have to give her each of those levels only one time, she gets it in whatever sequence she gets it, and we can't counterbalance that. Who's following that? Okay, so what we have to do then is we would give Maddie one particular sequence. She gets each of those conditions once and only once. And then Nina is up next, and she gets those conditions again once and only once, but she gets them in a different sequence. And maybe across these 2 people, we engage in our counterbalancing, so that by the time we look at the entire data set, okay, we've counterbalanced. But for any one person, the counterbalancing was said to be incomplete. Who's following that? Does that work for us? And we'll just contrast that with the rest of what Maren had to say, and that was in the complete design, we can give each person each level of the independent variable, but they get that now many, many times. So if we have levels A, B, C, and D, Maddie will get all of those, but she'll get them many, many times, such that we can actually give them to her in one sequence the first time through, then we can alter the sequence the next time through, alter it again the next time through, and even within Maddie's performance, we can now balance the sequence of presentations. Okay? So it's completely balanced because even for any one individual, it's balanced. Here, we're relying on the balancing to occur across the ensemble of people that we have, or participants. Who's okay with that? Okay? So all of this is still a within-subject design, but we almost have a between-subject-like aspect of this incomplete balancing because we're doing the balancing across participants rather than within a participant. Okay? Okay. All right, wonder if somebody wants to help us out with this. Potential pop quiz question, back to block randomization. We've talked about that once before. How might we use that in repeated measures designs? And we're getting a little prompt here from Sackheim. Anybody want to help understand block randomization in this study? Okay, we'll go with Kip.
Well, with the repeated measures design, you want each participant to experience every condition of the dependent variable.
Okay.
And that can be helped with
Okay.
Just to ensure that you get the same amount of trials of each condition.
Right.
And not have these random sequences of, let's say, all of the R's or all of L's.
Okay, really good. All right, so we are going to engage in block randomization, and Kip gave us the reminder that in block randomization we ensure that each condition is presented one time before any of the conditions is presented twice. Okay, and that's a nice way of controlling for practice effects, such that if there is some variation over time because we're getting way better, we don't get better in just one of the conditions, we're distributing the conditions across time. Also, if you're getting worse over time because you're fatiguing, again, we're distributing the conditions across time. And so what we can do is make sure that we get a right, a left, and an original picture here, one version of each before we get a second in any one of those conditions. Okay? So hopefully this makes sense to folks. How many people are familiar with this kind of stimulus? You've seen this before, or you understood it anyway from the readings? How many people are not so sure what's going on there? It's okay if we're okay. A few of us are not so sure what's going on in that particular face manipulation. Somebody want to try to unpack it for us? How that chimeric face, as it's called, is described? Well, why don't we go with Sasha, and then we'll go back to Jenna.
I think it seems like the middle one's the regular face.
I think so, yeah.
It's like made up of like both like of the right side,
Uh-huh.
and the left one is made up of the left side of the face.
Yeah, right.
But I don't understand like how that all connects. That's what I'm confused about.
Oh, okay. So maybe Jenna wants to say a little bit more. Maybe that you just.
That was what I was going to say.
Uh-huh.
But basically, like, if you want to get a sense of how people respond to those various spaces, then that's why you want to use that block randomization.
Okay, and go ahead, Meg.
Within like the table, the R, L, and L correspond to like when you're just like using the right side,
Uh-huh.
just using the left side, and then I don't know if
O is original, the original picture, right?
original
Okay.
image. They're making sure they have the participant like they show like one of them like once, or they show them a different one the second time.
Yeah. Okay. So that's our block randomization. And Mira has something else to add.
Well, I just have a question. What are they measuring when they're showing these?
Good. Okay. So they actually they take a few different kinds of measurements here. One idea is this notion that maybe it's the case that we have greater emotion in one of our hemispheres than we do in our other hemisphere. And to the extent that might be true, then it might be that we get contralaterally greater emotional expression. Okay, so if you believe, for example, that we have greater emotional neural responses in our right hemisphere, that controls our left facial expression. So what we can then say is, well, what would happen if I had two versions of my left side of my face versus two versions of the right side of my face versus the original face, which has a left and a right side. So we can show you these pictures one at a time, and we can ask you to make some kind of emotional rating. How emotive is that face? How neutral is it? We might have a particular expression that might be disgust right there. So which, on a scale of 1 to 10, how much disgust are we experiencing here, or is being exhibited here? How much disgust is being experienced here, and how much disgust is being exhibited here? And we can see if, after presenting these to many different folks in a block randomized design using repeated measures, display, is it the case that one side of the face tends to be more emotionally expressive than another? Okay? Who's following that logic? Okay? All right, so that would be the kind of idea. There are variations on it, but that's usually why we use these chimeric faces. Okay? And it gives us a nice opportunity to talk about block randomization. So what can happen is you could have imagined that it could be the case that Maddie is just doing 1, 2, and 3, and that Nina is doing 4, 5, and 6, but it also could be the case, and this was actually the way that it went, we had many different kinds of faces, and we would have Maddie running through 1, 2, 3, and 4, 5, and 6, and so on down the line. So it was actually, in the real study, it was balanced within a participant. We call that the complete balancing. Okay, let's go on. And let's see if somebody can just help us out with what might be one of our simpler ones. Can somebody explain what an ABBA design is? Anybody want to help us out with that? ABBA. Okay, thanks, Maddie.
You give the conditions in a specific order, so you give the first one, A, and then A, instead of like doing randomization, you could have like long strands of A's or B's.
Okay, really good. So actually, for those of you in the back who didn't hear all of that, Maddie has almost given us the answer to 2 questions here. She's talking about having just 2 conditions. The first one is A, the second one is B. In the video, I talked about the possibility of using rote memorization versus the method of loci. Just for fun, who remembers doing a memory section in Psych 100? You talked about memory, or maybe it was called cognition, and you might have done some memory exercises where they gave you simple rote memorization as one of your techniques, and then they might have given you some kind of memory device. Does anybody remember doing something like that in Intro to Psych? They might have given you the method of loci or a rhyming scheme that you would use to memorize, something along these lines. So it could be that this memory trick is condition B and rote memorization is condition A, and we ask people to respond in rote first, then memory trick, then rote. That would be A, B, B, A design. Maddie also alluded to why it might be more advantageous to use the A, B, B, A design, or when it's more advantageous to do that. And she was saying that you can sometimes have these long strings that come up, A, B, B, A. You might get A, B, A, B, A, B many times. You'd want to control that. If you have a very limited number of presentations, you want to make sure that you get to counterbalance maybe within one participant, but you don't want to let the randomization take root. I do want to talk a little bit about anticipation effects. Maybe this is obvious, but if you're regularly going A, B, B, A, it might be the case that the participant gets to understand that sequence, right? And they can almost anticipate what the next stimulus is going to be, and they're almost forming their responses before the stimulus has come up. And now you've got these demand characteristics that you might not want to have. So you don't want to have a very predictable kind of stimulus set. So sometimes A, B, B, A can get in the way there. Who's okay with that? That there are anticipatory effects that can become very obvious? Okay, love this thing, the Latin square. Absolutely love the Latin square. I think it's one of the more elegant things that experimental psych has given us. Can somebody identify 2 ways in which a Latin square balances practice effects? Okay, we'll go with Jenna.
Well, the first way, so it just randomizes the conditions. And the second way is that it ensures that each condition appears in each ordinal position. So each condition, so an A is going to appear in the first place, the second place, the third, and the fourth at some point.
Okay.
And they're also each condition is also going to be preceding and following another condition at one time.
Oh, okay, really good. So Katie had her hand up also, but maybe that was everything that, okay? So the idea here is if we think about administering this as condition 1, 2, 3, and 4, we could have gone from top to bottom, but I'll just go across as this is what you receive first, this is what you receive second, third, and fourth. Any one of these letters will appear in each ordinal position, okay? And that happens exactly one time. So A will appear in position 1, 2, 3, and 4. And if we were to go through the whole thing, we could see that B appears in 1, 2, 3, and 4. Okay, so each condition appears in each ordinal position. So that helps. The other idea is that each condition immediately precedes each other condition exactly one time, and it immediately follows each other condition exactly one time. So that's an important feature as well. And it does take a while to develop these, right? So it's nice that these are published and available online and so forth, so that if you're running one of your own studies and you want to take advantage of how the Latin square nicely controls for these order effects, you don't have to try to reinvent this wheel each time. And they have them for different size experiments. This happens to have 4 levels, but you can find a Latin square for 3 levels or for 5 levels or for 6 levels. You might imagine that they get a little bit more complicated. Okay, who's following that? The advantages of the Latin square? Really quite elegant. Love that about our field. It's one of the things I think we do well. Okay, can somebody help us out with this notion of differential transfer and what a solution to this might be? Anybody want to help with that? Okay, we'll go with Maren and then Sasha.
It's being exposed to one condition, it might affect another condition.
Okay. Okay, so being exposed to one condition might affect another condition. Okay. All right. Anything you want to add to that or build on that? Good. Okay.
Something that one condition has consequences when it's exposed to another condition.
Okay.
And a solution would be to use not to use a differential system.
Right. Okay. So what we might do in this case, if we do have carryover effects, if learning something in the first condition now is going to affect behavior in the second condition, and if that turns out to be problematic, then we might just say, you know, the best way out of this is to just administer that independent variable in an independent way between subject's matter rather than within subject's matter. Who's following that? Does that work for? Okay, really good. This is often the case with drug treatments. If you don't know how long it takes to have the drug metabolized through the body, then sometimes it's safer to go with a experimental group and a control group and not take a chance that you've allowed this washout period. Before I came to Denison, I spent 4 years at Columbia University, and I did have the opportunity to work with some psychiatric patients. And in one case, I had the chance to work with some people who were suffering from schizophrenia, and we were trying to look at them when they weren't on their meds. But we couldn't always tell. We knew that they were off of their meds for a certain interval of time, but we couldn't tell whether the drugs had been completely washed out of the system or not. We had to make our best guess about that. So one of the problems of differential transfer or carryover effects. All right. So that was a lot of pop quiz questions, but it's fun to have the group respond to those and see what we've gleaned from the videos. Any questions or comments on any of that before we go ahead and look a little bit more precisely at the t-test in the bi-level design? Yeah, please.
I don't really understand of why the ABBA design is more advantageous than the block randomization.
Okay, so what can happen is, what's really nice about ABBA is that we can definitely control the sequence of events, right? And we can do counterbalancing very precisely, even for a very, very small number of presentations, right? We can have ABBA. If we go with some other kind of block randomization or other kind of randomization scheme, you might remember that if we have a purely random scheme, then what we would need would be a really long set of numbers so that we can balance things out, because in a purely random scheme, we would have strings of numbers. Does that work for you? We might get strings of AB, 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 right? Okay, we get a long string there. And if we're going AB, 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 it is certainly true that we're getting an instance of A and an instance of B before we get our second instance of either A or B. But if we keep on going AB, 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 A is always leading, right? And it might be that if we had many, many opportunities to engage in block randomization, we'd finally get some BAs, BA, BA. But we really can't take a chance when we have only a few presentations to make. Maybe because we're constrained by time, maybe because we're constrained by the number of participants that we have. So we can, in the video I use the expression, we can grab the bull by the horns and make sure that we get AB and BA by using that kind of design. Does that help? Yeah? Okay. All right, something else. Okay, why don't we go ahead and talk a little bit about the repeated measures design. We've previously done t-tests. In fact, we did a computation, I think, on Friday. We went in and computed thing 1 and thing 2 in our denominator. And now we're trying to do the same in the case of the within subjects design. And fortunately, this turns out to be, in this particular case, it's a little bit easier computationally for the within subject t-test. It's actually an easier formula. And this is on the back side of what we used the other day. So if you have this one lying around, you can see that it's actually a simpler formula. We'll take a look at it, and then maybe in a few minutes we'll go and we'll compute it. Here's the T-statistic. It still adheres to the same distribution. So it's the same T distribution. It's almost bell-shaped. These are just a little bit fatter than they should be for a bell curve, but it still looks like a bell shape. It's not a pure Gaussian. And the idea is that we can zoom in on these two components, and we are still going to get something like a between subject difference versus a within subject difference. In the numerator, we have this D bar, the mean difference on the scores. Okay? So if we did have, say, 2 different ball color conditions, we had a white baseball and a red baseball, we could simply difference those scores for Marin. We'd have her different score. We could difference those two for Nina and for Maddie, and we'd have a whole list of different scores, and we could take the average of those different scores. And that would be the numerator of our T-statistic. What would the null hypothesis predict about that difference? 0, okay, right? So mathematically, if it were the case that ball color really didn't alter anything, then Marin should be getting about as many hits in the red ball condition as she is in the white baseball condition, and we're going to get some number close to 0. Nina will have some number close to 0, and they might not be exactly 0, but they're going to average out to be something like 0. Okay? On the other hand, if red really is, for example, a lot easier to hit than white is, then no matter who's doing the hitting, we should see some tendency for red to be generating more hits than white, and that would give us a difference that's departing from 0. Who's following that? Okay. All right, now what happens is we also have to get the denominator term, and this is actually an easier denominator term than that crazy thing that we had to do the other day this monster that we had for thing 1 and thing 2, right? We had to divide it into those two components and take the square root of their product. That was a little bit crazy. Here, we're back to something like the standard error. Show of hands who remembers doing the standard error before? Okay, right? And that was simply the standard deviation divided by the square root of n, where n is going to be the number of pairs of scores that we have. Okay? So we have this mean over the standard error, and then we have our degrees of freedom, which will be n minus 1. Here, again, n is going to be the number of pairs of scores. Okay. So there's only one assumption that underlies this, and that's kind of interesting because we really do have two sets of numbers, right? We have the numbers from the white baseball condition, the numbers from the red baseball condition. So you might think that we have an equal variance assumption or something like that. In this case, actually, we don't, because what we're really analyzing is one set of numbers, and that one set is the difference scores. Okay? So we have only that one, and all that we request of that is that if we have many such scores, they'd be at least approximately Gaussian distributed, which is to say they form a bell curve, the normal curve. Okay, one more time, some pros and cons associated with any within subject design. Anybody want to help us out with pros and cons? Okay, we'll go with Giselle.
They remove, the pros is that they remove consistent individual differences.
Good. Okay, they remove consistent individual differences. That's the sort of the main one. Some other pros or cons? Thank you, Maureen.
They're more efficient and they use less participants.
Okay, they use fewer participants. I think Hannah had a hand up also, but
Yeah, that was also my pro, but con is the carryover effect.
the carryover effects, right? Okay, so it could be the case that there are carryover effects, and we need to be aware of maybe what kind of demand characteristics we're establishing. So we have to think that through. We're always bound by critical thinking in these items. Okay, let's see if we can take a look at how this might appear on a computation and what we might do in Excel, what we might do in SPSS, and then we'll spend the remainder of the session actually doing that. So here is the statistic that we just saw. We've got the difference scores. We're going to take the mean of the difference scores, and then we're going to find the standard error of that. And that ratio will give us the t-statistic, and we'll use t-inv and t-dist as we have before to put the t-value that we observe into some kind of context. Where is this thing falling? As I think Jenna mentioned a moment ago, the null hypothesis will be calling for a 0 difference, and we'll see if we get something that departs significantly from that prediction of 0. All right, and then we can also take a look at what we would do inside of SPSS. We would be analyzing, and we're still comparing means, and we're going to go to the paired samples t-test, and we'll take a look at the output, and we'll see if we get a t-value that has a sig value less than 0.05. Okay. All right, before we get into the ANOVA, why don't we go out and try to do a manual example of a t-test, just for a little bit of context, of course. Our research cycle is here. Okay, we have different kinds of designs that we're using. We're talking about experiments contemporarily that are within subjects or repeated measures experiments. And one of our data analytic techniques will be the within subject T, and in a few minutes the within subject ANOVA. So if you can open up the item that says within subject t-test inside of our practice folders. I'll give you a moment to get out there. And while you're doing that, I'll set this up. And maybe, too, I'll try to remind myself to always highlight this and go to a larger font so that people in the back can see it a little bit more clearly. I think 14 works better for the folks in the back. How's that? Yeah? Okay, we'll make that a little bit bigger. And I'm going to remind us of something that we mentioned early in the semester when we talked about the advances in technology in psychology, something called TMS, or transcranial magnetic stimulation. Who remembers hearing about TMS? Okay, all right, so I might have used Maddie's head. I don't remember whose head I had, but the idea is that we put this magnetic device to her head and we zap her, and we see if we get a change in behavior while she's being zapped. And we have some control over where that thing is positioned, and it might give us some information about what portions of the brain are controlling what kinds of behaviors, thoughts, and feelings. Okay? Interestingly, when I was working at Columbia University, some of the folks down the hall from me were psychiatrists. I'm a psychologist. These folks were psychiatrists, and they were working with folks who were clinically depressed. And they were using TMS as a very low voltage method of doing ECT, or electroconvulsive therapy. Who remembers hearing about that? Electroconvulsive therapy? It's a rather strong treatment that we try to avoid because it has all kinds of nasty side effects. This TMS really is very mild. You can zap yourself with this. It feels like you're plunking your head, and it doesn't really hurt. It doesn't have any long-term negative effect, and yet we're able sometimes to elevate mood with this through reasons that nobody really understands. We know that it works for a good fraction of patients, but nobody really understands the mechanism by which it works. Same thing for ECT. It's not fully understood why electroconvulsive therapy works, but for some folks it does, so we continue to use it. Okay, let's go with our very simplistic null hypothesis statement, which will be HO. You yell it out. It's going to be in the population, and what happens? Okay, not all means are, all means are equal. Okay, and we can copy that down, change the HO to an H1, and we can say that not all means are equal. Okay. And so what we're going to do in this repeated measures design, instead of having a group that's getting TMS and a group that's not, we're measuring some kind of scores, depression ratings, before versus after TMS. So we're hoping that we get a decrease in depression ratings. Okay? So as you might remember from our T, and here it is, you can have this in front of you if you like, we need to get some difference scores first, and we need to take the means as well. Okay, so why don't we go ahead and begin just by taking the difference scores between depression ratings before we administer TMS versus the depression ratings after we administer TMS. So we're going to say here the difference scores, or just difference, or even diff, will be equal to the before score minus the after score. So I did C7 minus D7. Maybe it's better if I do this. Does that help? Only a little bit? Okay. C7 minus D7, when I hit enter, I wind up with a score of 4. Who can corroborate that number? Okay. We can copy down that spatial relationship, and now we have a list of different scores. And then as our formula calls for, this is going to turn out to be the numerator of our T statistic. I can now get the average difference score. Okay, and I happen to notice, by the way, that those different scores were non-negative. They didn't have to be that way. The null hypothesis would have called for a 0 difference score. We have a non-zero. We'll see if this turns out to be big enough. But at least we have a positive difference score. It appears that they're going in the right direction. We'll call this the mean diff. Okay, a couple of different ways that we could go here. We could actually just take the standard deviation and the standard error, but let's just see if we can remind ourselves what that was like so we can keep those neural networks nice and warm for us. We'll get here the sums of squares. Okay? And to get that first, we need to get the difference scores from the mean. So this will be something like the score minus the mean. Okay? In this case, we're actually doing the difference score minus the mean. So that's going to be equals this 4, that's our difference, minus the mean difference. Okay? And I wind up with a 0.57. So that was the 4 minus that 3.4. Okay? I will also now go ahead and freeze that cell so that I can pull it down and take advantage of the spatial relationships inside of Excel. So I first get the different scores, and then I get the extent to which any one of those different scores departs from its own mean. Who's got that? The workforce? Okay. Anybody want to remind us what the next step is if we're trying to get to the sum of squares? Okay, so we're going to take that same quantity, s minus m. So the neighbor to the left in this case will be squared. We'll say equals that person, so to speak. And we'll square that. We get a 0.32. We'll drag that on down. So now we have the original difference scores. We get their deviates and the squared deviates. Okay? And now we can take the sum of those squared deviates, and we wind up with an SS for our difference scores. And I come up with a 31.714. I'll take just a little pause here and see if people can raise their hand if they can confirm that number. Okay, we'll give folks just a moment to catch up. Is anybody confused by that? Been doing that one for a while. Okay, so that's our sums of squares. Now what we need to do is convert the sums of squares to some kind of variance. Okay, so we can get the variance of the different scores. Anybody remember how we do that for a sample?
Divided by n, or sorry, the sums of squares divided by n minus 1.
That's exactly right. Okay, so Janet's got it. We're going to take this sums of squares, and we'll divide that by n minus 1, where n would be the number of pairs of scores that we have. We have 1, 2, 3, 4, 5, 6, 7 pairs of scores. So you can put in parenthetically 7 minus 1, or if you just want to put in a 6, you'll wind up with a 5.287 as our variance. And I'll see how many people can confirm that number. Okay. How do we convert a variance to a standard deviation? Anybody remember that trick? That was a mantra. Square root, okay, right? So the standard deviation is the square root of the variance. Who remembers that mantra? Okay, so it's been a little while since we said that. We can now take the square root of our neighbor to the left. Okay, and we have our SD, our standard deviation. Okay. So now we have the mean of our different scores. We have the standard deviation on our different scores. Okay. Something else we can do now is begin to head over on this side, and we'll start working toward our T-statistic. We'll need to work with that standard deviation in just a moment. But just to set the stage for this and put it into context, we have our degrees of freedom equaling n minus 1. Okay? And so in this particular case, we have 7 pairs of scores. So this will be equal 7 minus 1, or 6 degrees of freedom. And hopefully people will see that from the bottom of this page. Everybody okay with that? Degrees of freedom, usually the easier computation that we have. Okay. All right, and then why don't we go ahead and start doing our numerator-denominator. Our numerator is going to be very simply our mean difference. So we'll say equals, and I'll click on the 3.4286. Our denominator, we almost have here, right? We know that it's the standard deviation. What else do we have to do to the standard deviation? Anybody recall? Right, divided by the square root of n. Okay? So divided by the square root of, in this case, 7. And I wind up with a 0.869 and some change, or 868, depending on how you round that. And I'll pause and just see how many people got that. Okay? All right, so now we have our mean, and we're putting it over some pooled variability. In this case, it's going to be the standard error. Okay? And then we'll go to T6. Okay, we'll go ahead and compute our T-statistic, assuming that we have 6 degrees of freedom. And as always, that's simply going to be the numerator divided by the denominator. And we wind up with a positive 3.94. So the null hypothesis was calling for a 0. We wind up with something to the right of that. We wind up with a 3.94 as our observed T-statistic. Okay, why don't we see if we can go ahead and get the T-crit value. That's one of the possibilities here. So the critical value for T. Can we yell out what command we would use? Okay, tinv, right? Tinv. Okay. And now the probability, can you help me out? What's our favorite probability? 0.05, okay. And how many degrees of freedom did we say? 6, okay, 6 degrees of freedom. So we had to come to a value that was plus or minus 2.44. That's how far away from 0 we had to be in either direction. We happen to be greater than that in the positive direction, so we can actually reject HO. Okay. And if we wanted to put this into some kind of APA-style statement, we might say something like the following. We might say T6 equaled, and we can put in the observed value of T. It was 3.945, I'll round it to. Okay. And we could say that the P is, in the old school, we used to say less than 0.05. We can actually now give it a very specific value. P is equal to, and we'll need to compute that value. Anybody want to remind us how we compute the actual value of P? T-dist. Okay, thank you. I'll go over here to do that. Equals T-dist. Anywhere that you want to find an open space is fine. So we're going to stick in the observed value of T, which was this 3.94. We had 6 degrees of freedom. And we're always going to assume 2 tails unless we have some other reason for going directionally rather than non-directionally. So we'll put in a 2. And we wind up with a 0.0076. So in our APA-style statement, we're telling the audience that we used a t-test. We had 6 degrees of freedom, and this is what we observed. The probability of getting that by chance is equal to 0.0076. Okay? And if you wanted to, you could say something like reject HO here. You wouldn't have to do that, but this much is really APA-style, and this is, sometimes it's there, sometimes it's not. Who followed that? Worked for us? Okay, so we got some different scores. We put the different scores in the context of some variability, and we're pretty safely away from HO. Okay? All right. Yes, please, go ahead.
What again is the difference between like the T-dist and the T-in?
Wonderful. Thank you for asking that question. And it will come up in the remaining portions of our semester, so thanks for getting some clarity there. Let me tell you what they have in common. They're both trying to extract some information from this hypothetical distribution of T's. These are always bell-shaped. Sometimes these are collapsing in or moving out a little bit just based on the degrees of freedom. And when you collapse them in or out a little bit based on the degrees of freedom, this value, the value that we have to beat, changes. That value for the T-statistic comes out of some kind of an inv function, in this case the T-in function. Okay? So that would give us the critical value. We need to have a T value bigger than that value. Does that work so far? And then on the T-dist, that gives us the observed alpha level. So one is the observed level of T, and one is the observed alpha level. Alpha is the probability of making a type 1 error. Okay? And those two are always inversely related to each other. As T is getting bigger and bigger and bigger, the observed alpha is getting smaller and smaller. Okay? All right. Okay, I wonder if we can save this, and we've got 5 minutes. Why don't we make a mad dash for it? Why don't we see if we can put these numbers into SPSS, because in the not too distant future, you'll be up on your next SPSS quiz. Some of you are going into psych minoring or psych majoring, and you will have to be able to move data around from this kind of a format into SPSS. So why don't we see if we can get it started? Can you open up a blank SPSS data sheet? We'll let you click on SPSS. And you can just open it up to a blank. It'll take a moment for that to come up. And we'll start in variable view, and we'll start to think about how we might define some variables so that we could run this analysis in SPSS. Okay. In variable view, does anybody remember a commonly used first variable for us? Yell it out if you know it. Participant? Okay. So if you're up and ready to go, you don't want to be in data view, you want to be in variable view. We'll go over to variable number 1, and we'll start out with some kind of participant. In this case, it looks like we had humans, but we could have had non-humans here. And what else do we do with our type usually? We change that to a string so that we can give our participants labels that are going to be starting with letters. We can actually type letters directly in. Okay? All right. Some other variable that we might have would be something like before TMS. And then we might have after TMS. Notice that we don't have a group designation. We used to fool around with these groups and we'd have group 1, 2, or 3, but that's when we had many different groups. Here we have only one group, and they're receiving all levels of the independent variable, which would be before versus after TMS. Who's got that? Okay. And now what we can do is come on over, and we can put in something like P1, P2. I think we had 7 of these, so we'll put in our 7 participants. Oops, excuse me. Okay. So now we're in data view. We've got a space for each participant in each row. And then what we can do is click over to Excel, and maybe we can copy and paste these raw scores. So I've got 7 scores before, 7 scores after. I've highlighted that whole bit. I can use a Control-C, get my ring around the rosy going there. And I can plop those in with a Control-V as in victory. And there they are. How many people have that? Okay. All right, that should work. All right, and then we have a really simple sequence to click on here to get our analysis going. We'll go to Analyze. We'll go to Compare Means. And you tell me which one are we using here? Paired samples, okay, right, because these scores are paired. We get a pair for any given individual. I'll let you click on that to go to our next screen. It's our paired samples. Okay. And then we have only 2 items to slide over. We have before and after. If you'll highlight those and slide them over, that's the one and only pair that we've got, so this really couldn't be simpler. And we click on OK. And out comes this t-test that we have, where we have before versus after TMS. Hopefully that looks like a familiar number to you, right? 3.4 and some change. That looks like a familiar number to you also, right? We had a standard error of 0.86 and some change. We wind up with a t-value of 3.946. And if we take a look over here, we should get a sig value of 0.008, which is what we had within rounding error. Okay? So once again, SPSS gets it right. All right, who followed that? That worked for us? Okay. So now we know how to move from Excel over to SPSS using a within subjects design. In this case, it was a t-test. We come back tomorrow, we'll finish off talking about the ANOVA, and we'll also go into some other ideas relating to the assumptions underlying the ANOVA and a problem that arises with post hoc tests. Okay, so I hope you have the chance to watch the video tonight, and I look forward to seeing you tomorrow. Have a great day.